Hello, my name is Kirk Barker, and I'm the product manager for the Movement SDK, for Presence Platform's Movement SDK on the Quest 3. It's our vision to take the physical movements that you make in the real world and to translate them into the virtual you. Now, we've named this presentation Optimizing for Gameplay with Body Tracking on Quest, because today we're not going to talk a lot about body tracking so much, how you take that body tracking and move it into animate characters so that you can tell a story. Because in reality, that's what it's all about. It's not just the body tracking that you want, but you want the body tracking to go into a character, an avatar, and create motion and movement that tells a story and involves people in your gameplay. So the Movement SDK introduced body tracking in Quest 3 with two great new features, one called inside-out body tracking and the other generative legs. Inside-out body tracking takes the sensors on the Quest 3 that are facing downward and uses it to pick up the upper torso. So it can track elbows and torso and hip joints and give you really good motion fidelity for the upper body. Generative legs takes either that or three-point tracking and extends that to give you a full skeleton for the rest of the body. Since we announced those at Connect in last fall, we've been working really hard to now take those basic tracking capabilities and make them easier to use. To take that and then, like we're saying here in this presentation, to be able to tell a story with it. So if you've ever tried to take a body tracking rig and move it into a character, you may have encountered a number of common problems. You may have seen the shoulders tear apart and the skin start coming through on the shoulders or the back or even the legs or the thighs. You may have seen the movement look okay, but then when your characters went to interact, they couldn't even clap their hands or do a high five with another character. Or it may be that those things worked, but you know, you had a 3-foot-tall character you were trying to animate, and when you pulled in body tracking and tried to make it work right, you had to make that 3-foot character a 6-foot character. Well, today we're going to introduce our deformation logic, which tries to take all of those common problems and solve them for you as you move from the basic capability tracking that you have in the Quest and Quest 3 products into your characters. Now, I'll go through several examples today. I'll show you some problems that we've seen. We've obviously done quite a few characters by now. I'll show you some of the problems that we've seen, how to recognize what those problems are, and then how to correct those problems with our deformation logic. So hopefully by the end of this talk, you'll feel confident that you can take body tracking as provided by the Quest products and use it to animate any character that you want, or at least any reasonable humanoid character that you want, and tell any story that you want. So a lot of today will focus on trying to create that narrative story, or at least the appearance of the narrative story that you would really like to have in your game or experience. So for those of you who aren't familiar with the Movement SDK, let me back up for just a second and tell you we're an SDK that's published as part of Presence Platform. We take 3 basic tracking services: eye tracking, face tracking, and body tracking, and we export those over OpenXR interfaces. We have bindings for both Unity and Unreal. We didn't put it up on here, but it's a native interface as well. So there's native Unity and Unreal bindings. And it's all publicly available now. We have GitHub samples. At the end of the presentation, I'll show you the links for all of that you can download and use on your own. Now, the thing about this interface and where the interface works is that we're taking basic tracking services. So what we provide across the interface, in the case of body tracking, is a human skeleton. You can take that skeleton to animate any character you want. We're not restrictive in that way. In fact, we don't even know what you're doing with it. So we're giving you the basic movement parameters that you need. And today we're going to talk a lot about how do you take those basic movement parameters and translate them into the characters you'd like to see. So first of all, the challenge. Now, this may come as just a big surprise for all of you, but people don't all come in the same size. I mean, look around you in this room today, right? You see tall people, you see short people, you see skinny people, you see not as skinny people. People are all different sizes, and you know, we need to take those movements as they're wearing the headset and map those into avatar characters. Now, the problem is worse than just different sizes, because not only are people different sizes, they're also different proportions. Now, you probably can't tell up here, but I have relatively long arms. Now this comes in really helpful in playing basketball, but it turns out that my arms are a little bit longer than the average person. Your arms may be shorter compared to your torso. You look at some people, it seems like they have a very short torso and very long legs. So all of us as humans are different in this way. Some of us have short legs, tall body, etc. So we have to take all those variations that we pick up from the tracking and then figure out some way to map that into the avatars that we have. Now here's the second surprise. Avatars also are of all different sizes and shapes. At least humans were constrained by human genetics or whatever it is, that we all have about the same size head and the same general proportions. Your humanoid avatars have dramatically different proportions. You look at this guy here, his head is about twice the size of a normal human head. I've seen certain avatars that we've tested with that their head was so big that the avatar itself couldn't reach the top of his head. Well, if the person that's animating the avatar is able to reach the top of his head and your avatar isn't, well, what do you do with that, right? So there's a lot of things like this that we have to look at in taking from all the different things of body tracking and moving into the target space. So let's look at the first problem that we see and the one I mentioned. I'm afraid this one may not show up too well on the slides here, but the first thing that we commonly see is because of the way the rig is mapped into the mesh versus the body tracking rig, as you start moving around or moving side to side, you'll see the outer skin of the clothing just tear through. In this particular example that we show here, the bottom of the collar is torn apart. So that dark line that you see in the left portion here is actually the skin coming through. Now this is a really minor example of this. We've seen cases where the entire shoulder blade is coming through, or you have pants and the entire leg comes through the pants. And so this is just one example and a pretty simple example, but that's the kind of the first problem that you see. On the left, you can see that you see the tearing. On the right, you don't with the deformation logic. Now, a common response to this is, wait a minute, that means your character is just rigged wrong, right? I mean, come on, get a better character. The issue with this is that, we're not the only body tracking solution out there, and you may have created this character to work across several different body tracking solutions. Further, you've made a big investment in all the artwork of these characters that you've created, and you don't want to have to be retouching those just to work with a particular body tracking solution. So it's incumbent for the body tracking solution that you have to adapt to the characters that you provide and not the other way around. So that's what we're doing with our solutions and the deformation logic that you'll see. Second major challenge, there's a trade-off between the integrity of the character and the positional accuracy. And what I mean by the integrity of the character is this character was created without really, in most cases, any idea that you're now going to try and animate it with body tracking. So the original proportions of the character and the character integrity is keeping it exactly as it looked when the artist created it. So we have character integrity, but then we have positional accuracy. And let me illustrate what I mean by that. So if you just have rotations, I'm going to use my arm to do this. If you just have rotations and I hold my arm up like this and I do a 90-degree rotation, you can say, okay, that works pretty well. If I had an avatar that was exactly oops, sorry about that. If I had an avatar that was exactly my size and just applied a 90-degree rotation to this arm, that would do exactly what I wanted it to do. But now let's imagine, and when I was thinking about doing this, I didn't think about the lapel mic, so I hope this doesn't cause you guys a problem. Think about this as if my arm was, 6 inches shorter and was here. So as I do that same rotation, right, you can see the position of that fist is very different. So with a longer arm, the fist is up here, right? And now if I rotate it, with a shorter arm, it would be over here. So how am I going to map that? Well, you may think that doesn't matter a lot, and it doesn't matter if you're just operating in empty space. But as soon as you want the character to interact with itself or with another object, suddenly positional accuracy matters. And we'll look at several examples of that as we go through. In this particular example, what's being shown here is on the character on the left, before we applied our logic to account for the actual position, when she clapped, her hands would just go right through each other like this. And I'm intentionally not clapping here because I don't want to deafen any of you. But her hands would just pass right through each other. Now, with the logic applied, we now pick up the positional accuracy, so as the person being tracked claps, the actual avatar claps. And that's the intent that we want. Now, this is bad in virtual reality. It's worse in mixed reality. Because in mixed reality, you not only have to care about the virtual positions that you're dealing with, you have to care about actually physical objects. I might want to reach out and pick up, presuming I'm embodied in an avatar, and pick up a drinking cup, or probably not a drinking cup because I've had a headset on, but you understand the point. In mixed reality, this problem gets even worse. So we care about positional accuracy, not just rotational accuracy, and because of that, we have to do a lot of fix-ups and make sure that things actually work correctly. Now, again, kind of going back to the whole title of this presentation, we're talking about telling a story, and we really want to question the intent and the artistic intent of what I'm trying to do. So as you consider putting your character into your environment, the first thing you're going to have to think about is what size is your character compared to what's trying to animate that character. You want that character like super huge? In the illustration on the right here, you can see that the character that was being animated is significantly larger than the actual person wearing the headset. So I have to scale everything up to, proportion everything up to account for the size. Now, if you had every avatar in your system, and that may be something you choose to do, make everybody about the same size so they can interact easily, look each other in the eyes, then that's one thing. If you can make them the average size of a person, then your problem is much easier. But if you want a big diversity of sizes and want a little, Yoda running around playing with a giant robot, then you've got some mapping that you're going to have to take care of. Second thing is the proportions of your characters. Now, again, I'm kind of using specific terminology here. When I talk about proportions here, I'm talking about body proportions. So here, what I'm saying is it may be important for your character telling for your arms not to be normal human arm length, right? Maybe your character has these long dangling arms that just to be important in your character need to be about knee length as he's running around. Obviously, I'm thinking a gorilla when I say that, but nonetheless. So let's say you want that versus a normal human length. If you need to preserve that proportion, then we have to allow you options for doing that as well and moving into those particular cases. The last point is how important for the accurate placement of certain character body components. Now, in this particular case, and later in the presentation, we'll talk about two in particular, the hip placement and the head placement. But the reason those can be very important for gameplay is that they may be parts of your body that are interacting with different elements of your gameplay. So think about this if you're playing soccer and you want to head the ball or do something like that, then you want an accurate position of that head. If you're playing, or doing hula or doing something like that or doing something with your hips, then you may want a much more accurate hip position. So you need to make that trade-off as well. So another complexity that we have is there is a difference between what we call a tracking rig and the character rig. And through the rest of this presentation, I'll use those terminologies, and in most of the slides you'll see two different versions, the tracking rig and the character rig. Now, the tracking rig is what we pick up from the sensors itself, right? So the sensor goes through a machine learning algorithm and it outputs a skeleton. That skeleton reflects the human body, and it's fairly anatomically correct. In this particular case, what you see is the spine here. I don't know if you guys can see that very well, but the spine is actually curved, like the human spine. Now, no character rig I'm aware of actually has a straight spine. I'm sure someone here can tell me wrong for some particular character, but most of them, the spine goes straight up and down. The second thing here is the pelvis. The pelvis is at an angle like the normal human pelvis is. Now, the reason we've done it this way is we use this character tracking, and we want the highest fidelity body tracking that we want for the human body because we have two different outputs for it. One is we may want to monitor your body in a fitness app or do something like that, and we want that positional accuracy very good. We want to know, is your spine actually curved or is it not curved, or are you curving your neck? The other is, and that's the case we're talking about today, is I now want to move it into an embodiment, and as I move it into embodiment, maybe I don't care about that real accurate spine. So I'm going to have to adjust some of that as we go forward. Now, the first set of changes that we're going to look at here are the rig rotations don't match, and those are the two I just talked about a second ago. In particular, there'll be, in our case, the spine will be a little bit offset, the hips will be a little bit offset, the neck will be a little bit offset. And in each of these cases, we're going to try and detect what type of rig is there, and from that, then apply an auto adaptation for you. So we're going to look at 3 characters over the next 6 slides and look at those auto adjustments we apply. You don't have to do anything for this. We have a one-click installation. It just takes care of it for you, and you move on from that. So we'll start out with our blue robot here, and as I introduce this one, let me also kind of tell you the format of this slide and also each of the subsequent slides in this presentation. So in each case, what we're going to do is present a slide on the, or a panel on the left, which is a forward view of the character. You're going to see 2 skeletons overlaid there. One is white, and you may have a hard time seeing that, but at the bottom there's a key. The white one is the track skeleton. So these are the body points that we're actually picking up from the sensors, and you'll see in each case what we've detected. And you'll see a big difference between those and the retargeted skeleton. The retargeted skeleton is the green skeleton that you see, and it's the bones after we've mapped them, and we've also applied deformation logic, and you'll see a difference in those as it goes forward. But they're what's going to actually animate the character, and they're going to correspond to, in this case, because it's Unity, the humanoid rig. As I mentioned, we also are on Unreal, so it's the mechanism rig there, but in this particular case, it's the, this mannequin rig in Unreal and the mechanism in Unity. Okay, so in the second panel, you'll see the same thing that you see in the first panel. It's just it's rotated at the side. And our reason for doing this is on some things, like if you look at the toe angles, or for that matter, the angle of the pelvis, you can see it different on the angled presentation than you can on the straightforward. And it's a little easier to see. So as we go forward, I'll point to one slide or the other slide to best illustrate the particular points that I'm referring to. And then finally, we'll drop both of the skeletons so that you can just see the mesh itself and how the mesh is rendered if I don't have any overlays for visualization. Okay, so blue robot, again, as I mentioned, this first slide I'm going to show you is going to be on just after bone mapping. And for those of you who don't know, bone mapping is just saying, okay, I have a bone in the track skeleton, and I'm going to map it to the same bone on the retargeted skeleton. But I'm not going to do anything fancy. I'm going to just take those and do it straight over. Now, in each case, I'm going to go backwards and forwards so that you can see the change. And hopefully, yes, that works. This is high tech. We can do this. Okay, so here's after the readjustments. Here's before. Sorry, I think I've got those backwards now. Here we go. Here is after bone mapping, and here is after the auto adjustments. Now, the differences that you'll see here are particularly around the hip area. You notice in the center slide, you can see it most, and on the final one on the right, where his hip has rotated out and forward and back. You'll also see it on the neck rotation. So you see it probably best in the center slide. You can see the neck is rotating as we move from one to the other. So that's a very common set of rotations we apply. Let's look at it with another character. Here is, again, just a standard character we've downloaded, and you'll see the same thing for it, right? So hip rotations, shoulder rotations, bringing it back to really preserve the creative intent of what you want to do. Now, that's all pretty straightforward. Let's look at it in one more character. This is a stylized, same thing. Here it is after the bone map, and here it is after the auto adjustment. So you see, going back and forth, you know, it looks like almost she's doing a little dance here or something. We've got the hips going back where they should, and everything looks okay. Now, those were all the easy ones to apply. Those we figure out, we apply for you. They're good, but you should be aware of them just in case that your particular character is rigged differently. We do leave an adjustment array at the end of the component that does this, so that if those adjustments don't work for your particular rig, you can always come in and do a mapping of, you know, any particular bone, any particular rotation, and any particular degree, and you can do up to 3 rotations per that bone so that you can get what you need. So that was the easy part of the problem. We just have dealt with rotations. We're now going to go to something more difficult, which is the human proportions are being different. Now, with human proportions being different, it's a lot tougher than just doing a rotation mapping. So let's talk a little bit about how the user interface works here. The methodology that we've chosen in each case is to apply a slider. So you'll see this done again and again, and it's very common in all game development, where we have a position that is the biasing towards tracked and another position that is biasing towards the retargeted rig. So in each case, the position of 0 is you want everything tracked. The position of 1 is you want everything for the rig, and we'll do that in each particular cases. This is broken down into the sections for the body, where you see the spine adjustments and all that, shoulders and arms and legs. There's one exception to this, which is not a slider, and that is where you see the spine translation correction, which is the very first one up at the top. It's a selection list where you say, hey, I want either accurate head, or I want accurate hips, or I want to do both accurate heads and hips. So let's look at a few of the deformations that we see with this. And go through it. So in this first, in this first example, we're going to go back to the girl that we were just looking at, and take a look at what happens after the auto adjustments versus what happens after the strong deformation. Now, here you can see, if I could get to the right slide, there we go. Here you can see a huge difference. Now, what's happening here is that this particular character was a very short character, and her original proportions are very much like you see here, which is a small upper body and a large torso. So what's happened is the track positions, which is what you see in the white thing, the person being tracked, his shoulders are about the height of her head in this particular case. So this is the chest bones that are coming across the top there in the upper white. And you can see it's actually much greater applied. Now, if I don't do anything, basically what I do is I stretch that character, and that character is now the same size as the tracking skeleton. And that's what you would see by default. If we apply our deformation, we then say, hey, let's bias this towards being accurate not on the tracking, but accurate on the rig itself. And so we'll bring those shoulders down, and then we'll adjust everything. Likewise, her hand and her arm movements are going to move corresponding to what that new position would be. So that's the basic high-level one, but let's drop a little bit and talk about the next application we'd apply, which is shoulders and arms. And so with shoulders and arms, we're going to use a different example. In each of these, I've chosen an example that best illustrates the problem, but some of these will be seen with any particular character. So we start out with our robot arms and shoulders, and this is a deformation value of 0. And here you can see there's a big difference between where the tracked rig is and where the retargeted rig is. There's two particular areas here you can see a lot of, the shoulder, at the top of the shoulder, and also in the rotation itself. So now, as I move to it being fixed, you can see that the tracked rig position is now moving up, and I'm sorry, the retargeted rig position is now moving back and up where those actual shoulder positions are. So if you wanted this character to be able to play a game and interact in your virtual world at about the same size as what your actual user is doing, then this would be the rotations you would want to apply. The other thing that you can see is the character integrity. If you look at the far right, on the far right, you can see he's got these big sloped shoulders, and it looks like, well, that looks kind of funky, right? So by the time we bring it back up and make it look more humanoid and really look like what it should look like, it's just a much better representation for the gameplay itself. Now, we did all of that simply by adjusting these particular weights that we have here as sliders, moving them from 0 to 1, and making a specification of which we would prefer, the rigged body or the retargeted body. Okay, let's look a little bit at legs. We have a similar type of retargeting that we want to do, but this time we would like to look at it on the legs, and we're going to move back to our knight to illustrate this particular problem. So this one is a little bit more subtle, but if you can see it carefully here, you can see that the white overlay on the legs are not at all the same as the green overlay. The green overlay is wider, so it means that the character actually has a wider stance than my tracked person. In this particular case, we're going to make the decision, hey, I really want the leg position to be accurate, so I'm going to put a weight on it, and I'm going to move back. And so you'll see the impact is that it looks from being a wide squatty position to being a narrow position actually following the tracked. Now, it might be reasonable for you to say, hey, that's cool, but I wanted the squatty position. Well, that's okay. Just move it back to 0, and you'll have that. The other thing that you'll see here are the toe weights. Oops, sorry. So if you look at this first position, and you can see this in the center slide, this character, when it came in, its toes are kind of angled up. Well, that's not what you want. You want the toes to angle down and to touch the floor, and so we applied a toe weight of 1. Next, we want to talk about fingers and hands. And you might think that this is an easy part, but this is actually one of the hardest parts of what we do. There are 5 reprocessors that work in our solution for retargeting the hands. And I'm showing you 3 of them here. The 2 that aren't opened up at the top are for wrist positions. But the 3 that I'm showing here, there's 1 for the left hand, 1 for the right hand, and 1 overall. Now with that, we've taken a particular character here. And this one is really an obvious change as you see as you move from the far right panel. So I'm going to try and focus your attention to the right panel and the hands. On the right hand, you see basically 2 fingers that are coming up above the gloves, and on the left hand, you barely see any fingers at all. Now look what happens after the retargeting. Now I've got these big hands that I'm really, this is the character that I want. He's got these long fingernails and really the character that I'd like to have. On the left hand, same thing. Now you actually see the fingers and it's coming out, and this is what you want. But look at the difference. I'm going to now direct you, I'm kind of going backwards on this. I'm going to direct you to the center slide. Remember, the white skeleton is the hand skeleton that's being tracked. So the human that was being tracked is that little white skeleton that's on the inside there. You can see that the character skeleton, his fingers are twice as long, or his hand is twice the size of a normal human hand. So how did we retarget this? I want to show you one other thing on this, which is the far left thing. Far left panel. So in the far left panel, look at the difference between the retargeting and the targeting. And you can't, I think, see this very well in the slide, but there's these 3 joints that are right here. So these 3 joints of the hand, the distal, the proximal, and whatever the other one is. What happened in the character was the bone that was from here to here got extended. It doesn't start until that first curve down there. So the whole white gets translated down and magnified up. And that's how that was accomplished. Now realize all this is going on in real time, so you're moving around, you're doing this, and it's all tracking, it's all working natural. And you may think, well, wait, that's kind of crazy, right? Because the hands are twice as big. Well, if I go to interact with something at that point, isn't that going to mess things up? Turns out the human mind is really good at accommodating for that. If you have big hands in a virtual world, you'll kind of operate to deal with big hands in the virtual world and pick things up. So the mind adjusts fairly quick. The next thing, and the last one I'm going to talk about today, is accurate heads and hip. Sorry, hip and head. So in this particular case, this is the case where I told you before, I may be really concerned in my gameplay about having an accurate head, or I may be really concerned about having an accurate hip. And so what do I do to really make that choice and make that forward? Well, fortunately for you, it's as easy as selecting that drop down. So if you say accurate head, we'll make that head accurate. If you say accurate hips, we'll do that. So we'll look at a few slides with those 2 changes. So in this one, the blue robot, same thing as before, has accurate head selected, and now hips. So head, hips, head, hips. Now what's interesting here is because the actual height of that robot is about the same, you don't see a big difference on head and hips from where the head height is, but you see a dramatic position, but you see a dramatic position on the hips. And the reason for that is if you look at where these hips are, the retargeted, or the tracked hips, are significantly in front of those retargeted hips in that mesh. So when I move to hips and it aligns those, it aligns not just the height of the hip, but also the position of those hips. So it drags that whole skeleton forward, and it looks like it's actually moved forward, but in reality, it's just aligning those white lines from tracking to those green lines from the retargeting. Let's look at that in a different character. So here we see it again in the night image. Same thing, accurate heads and hip. Now here, I don't know if you can see that left image, but when we started out on accurate head, it turns out that white line for the hips is below the retargeted line. And so what that means is that as we shift between those two, it basically makes him shorter. Finally, we'll do one last one, which is the stylized accurate hips. Now remember, this character is dramatically different, and so on her we see a huge difference as we move from head to hips. And finally, if you just want both, we give you that as well. So the thing is, when you want both, if you want both accurate heads and hips, the only thing we can do with that is now stretch out that character model, right? Remember, in the character models before, it had a little squat torso and long legs. Now we have to stretch that out, so you've destroyed some of the character integrity, and that's where we go back to trying to make a good game-telling story. And I've been told I'm out of time, so I'll try and cut this off fairly quickly. This is all totally public. It's available on GitHub. Feel free to download it, take a look at it. If you have questions, catch me after this, and I'd be happy to answer any questions I can. If not, you can also post issues to the GitHub link above. And thank you very much for all the time and attention that you provided today.